The next topic is coherent systems. The motivation for coherent systems will be driven by this example. Here is what I'm describing as a useless structure function. Phi of x equals 1 minus x. So let's pretend we just have one component in a system. In other words, the system is the component. If we let phi of x be 1 minus x, then when x equals 1, which is when the component is operating, phi of x will be 0, which says the system has failed. Likewise, when x equals 0, phi of x will be 1, which says the system is operating. So we have a failed component giving an operating system and an operating component giving a failed system. That is a nonsensical structure function, so that's one we really don't need to consider. So the notion with coherent systems is we want to devise some criteria associated with phi of x in order to, number one, eliminate unrealistic systems like the one in the example. And second of all, when we put in these criteria, it will allow us to derive some mathematical results. So let's start with a little bit of notation here. When you see this vector right here, 1i comma x, what that says is there is going to be a 1 in the ith position of the vector, and everywhere else there will be a generic x values are in there. Likewise, when you see the vector 0ix, it says that there will be a 0 in the ith position and then generic x's elsewhere. We'll be using that particular notation on the next slide. So here is a definition. The ith component is irrelevant to the structure function phi if phi is constant in x sub I. Otherwise, the component is relevant to the system structure. So let's look at this system on the left that has an irrelevant component. If you think about the four possible system state vectors, you'll realize that nothing matters except for the state of component 1. Component 2 is irrelevant. So I am going to write that in here. The irrelevant component in this system right here is component 2. Now here's another system, component 1 in series with components 2 and 1. Now notice we have repeated components here, so even though it's just a two-component system, that is, there's two components, whatever the state of component 1 is right here, that will also be reflected in the state here. So those either are functioning together or are failed together. Well, if you think about this system as well for a few minutes, you will realize that component 2 is once again irrelevant in this case. Its state doesn't matter. The only component that matters is component 1. So for both of these systems, I could write the structure function phi, which is a function of x1 and x2, as just x1. In other words, x2 doesn't show up anywhere. If component 1 is operating, those systems, both of them, are working. If component 1 has failed, both of those systems have failed. So those are examples of irrelevant components, and that's going to be half of the definition of a coherent system. So what we want to do is we want to consider a subset of all possible systems of n components that are known as coherent systems, and here is the definition. A system of n components is a coherent system if phi of x is, there's two pieces to this, increasing in x, and furthermore, there are no irrelevant components. Now, this is going to drive the mathematicians crazy, but when reliability people use the term increasing, what they really mean is they mean non-decreasing. And likewise if they use the term decreasing. So you've got to watch out when you hear that word increasing. What it really means is non-decreasing. Here is the intuition associated with a coherent system of n components. First of all, replacing a failed component by a functioning component does no harm. And that's this first condition right here, that the structure function is increasing in x. And then the second condition, that there are no irrelevant components, that's the same as saying phi uses all of its arguments. It isn't like the two systems that you saw on the previous slide where they did not use the argument x2. When you see phi of x increasing in x, which is our first condition, you can write that a little more mathematically in this form using our new notation, which is to say phi of 0ix is less than or equal to phi of 1ix for all I, and that means for all I equals 1, 2 through n. There are a number of results that can be proven concerning coherent systems. Here's one of the very basic results. It says the following: if phi is the structure function of a coherent system of n components, then the product of the xi's is less than or equal to phi of x is less than or equal to 1 minus the product from I equals 1 to n of 1 minus xi. You will notice that this left-hand side, that is the structure function for a series system. And you will notice that this right-hand side is the structure function for a parallel system. So this particular theorem says any way that I arrange components is going to fall somewhere between that of a series system and a parallel system of those same n components. And that's still another way of saying the series system is the worst possible arrangement of components and the parallel system is the best possible arrangement of components. So the intuition is coherent system performance is bounded below by a series arrangement of components and bounded above by a parallel arrangement of components. Here is a second well-known result to reliability designers or design engineers, and it is what can be done to increase the system reliability. Let's say we design a system in this particular arrangement right there. So we have component 1 in series with a subsystem consisting of components 2 and 3 in parallel. And let's say the system reliability for that particular arrangement is not high enough. We want a higher system reliability. Well, as mentioned before, one thing you can do is place things in parallel. So we procure another set of 3 identical components. And on the left is something called component redundancy. What it says is leave the system in place and take each of the components and in its particular position in the system just put another identical component in parallel with it, and that's called component redundancy. On the right, I still buy another set of 3 components to increase the reliability, and in this particular case what I do is I basically replicate the whole system. And the question is it smarter to do component reliability on the left, or is it smarter to do system reliability on the right? Now, one subtlety here, you remember that in k out of n systems, like when we wrote down the 2 out of 3 system, we used something called repeated components. And when you saw a 1 for component 1 in those two positions, well, that's really one component, and those are functioning and fail at the same time. This is quite different in that this is a component of type 1, and this is another component of type 1, but they are two different components physically. So both of these systems here are 6-component systems, and if you want to know what's the better of the two, you could go through all of the 2 to the 6th different system state vectors, and that might give you a clue which arrangement is better. But we can prove this in a theorem, and the result that you're going to see on the next slide says that component redundancy is always preferred to system redundancy if the system allows it. So here is that result stated as a theorem. Let phi be a structure function for a coherent system of n components. And there are two parts to this theorem. The first part says, for any state vectors x and y, this left-hand side here, which corresponds to component redundancy, is always going to be better than the right-hand side, and this right-hand side corresponds to system redundancy. And that is the theorem. Furthermore, this greater than or equal to is going to be strictly equal when you're looking at a system with phi of x that looks like this, which you probably recognize by now as a parallel system. That part A takes care of our component redundancy being superior to system redundancy. There is an analogous side to this theorem that looks like this. Phi of x1, x2, x1, y1, x2, y2 through xn, yn is less than or equal to phi of x, phi of y. And equality holds when you have phi of x corresponding to a series system. So part A is the key one for design engineers, and that says component redundancy is superior. Here's the proof. Now this proof that you see here is going to be part A of the theorem only. And here's how it goes. Since 1 minus xi, 1 minus yi is greater than or equal to xi. Now why is this true? Well, if we look at xi all by itself, that's the right-hand side. Why is the left-hand side always going to exceed that right-hand side? And the reason is the left-hand side of the inequality corresponds to a two-component system that includes xi. So all you're doing is placing a component in parallel. That's always going to improve things. So we know that that is true for I equals 1 to n. And phi of x is non-decreasing because we've assumed that the system is coherent. And this implies that this left-hand side right here, and that left-hand side corresponds to component redundancy as given on the previous slide, and that is always greater than or equal to phi of x. So you can think of this as the original system, and there is going to be no harm done by simply placing these in parallel. Adding components in parallel is not going to hurt things because your system structure function is non-decreasing. Well, by the same type of thinking, if you compare just basically the B components from the picture 2 slides ago, and you put the A components in parallel with them, that's going to be better as well. Now, since the left-hand sides of these two inequalities are greater than or equal to the two right-hand sides, we know that the left-hand side, and this left-hand side here, of course, is component reliability or component redundancy, that's going to be greater than or equal to the maximum of phi of x and phi of y. Whichever of these two right-hand sides is larger, it's going to be greater than or equal to that. But we know from parallel systems that when we take the maximum of two values, that's the same as 1 minus phi of x, 1 minus phi of y, and that concludes the theorem, the proof of the theorem, that the component redundancy will exceed the system redundancy. Now, to finish off part A, you would then take the parallel system, simply plug that into both sides of the inequality. They both would reduce to this quantity right here, and that would take care of part A. So the reason only part A is proven here is that that is the one that is used in system design.